So today I am going to explain combustion analysis, that is 2D combustion flow analysis. So I will explain both axisymmetric and axisymmetrical swirl cases. So the first one, so here I have just shown a simple combustor model. So there is a air inlet, okay, so there is a air inlet, then perpendicularly I am injecting the fuel. Fuel can be simplest one will be the hydrogen, or you can take the hydrocarbon fuels also. That is, if you take the hydrogen, there will be only a water vapor formation. If there is a hydrocarbon, you can see water vapor, additionally CO2, both you can see, okay. So anything you can use it. So air and fuel I have taken separately. Above and below there is a wall, then it is open to the normal atmospheric condition. So this will be the simplest combustor model you can simulate. And before going to some concepts, I will explain how we will change the boundary condition for the cold flow and the hot flow, okay. So in the cold flow, that is just flow through duct etc. and all. If it is incompressible, we don't enable the energy. If it is compressible flow with density variations, the supersonic flow and all, we will enable the energy also. Then some viscous model we will choose, depends upon that our application. And in this combustion, additionally we are enabling this species, okay. So in the species, you see there is a species transport, then non-premixed combustion, premixed combustion, partially premixed combustion, like the different models are there. The first model, it is to simulate just the some hot gas mixing property. If you want to simulate, we can check this species transport to different methane and air with different high temperature something. If you want to see simply the mixing property, for example combustion gas as it is passing through the CD nozzle, if you want to simulate, you can go for this species transport. And if you want to simulate the combustion process where there will be a reaction, then you should go for this non-premixed, premixed, partial premixed, this kind of thing, okay. So in this species transport, there is no reaction, there is no combustion, okay. If there should be a reaction and combustion, then you have to choose these three. So I am going to take air and fuel separately, so I am opting for the non-premixed combustion, okay. So in that, if you check the second boundary, you can define the mole or mass fraction of the oxidizer and fuel. Normally this oxidizer value by default it will be filled, okay. Only this fuel molar mass fraction you have to define. For example, there will be H2, then they may mention the methane, like that few fuel they will mention. So if you want some other fuel, then you can type here, okay. So ethane and propane, something if you want to type, if you want you can type here. Or if you want to know what are all the different fuels available, you can click on this list available species. Then in this window you can see around over 700 fuel combination, species combination you can get it. From that you can choose, you can type here, you can add, okay. So for example, here they have just taken the H2, that means you have to type 1 for the fuel, okay. So that next to the H2 you have to enter the 1. Instead of H2, if you are choosing the CH4, then next to the CH4 you have to define the mole fraction 1. H2 should be 0, then here you have to define the 1, like that. Depends upon the fuel you are taking, the mole fraction or mass fraction you have to define, okay. So this in the boundary tab, we will already the oxidizer the mole fraction is defined. Only the which fuel you are choosing, that mole fraction alone you have to define. Then the next one, table. First we discuss the boundary, now the table. In the table, just you have to click on this calculate PDF table. PDF means probability density function. So what it will do, depends upon that oxidizer and fuel we have chosen, there will be already library of all the list, right. So from the library, it will calculate and give all the species, what are all the reactant and products involved in this combination, everything it will list here, okay. That is, without this calculate PDF table, if you open this material tab, you will see only air and aluminum, right. Fluid as air, solid as aluminum, these two only will be visible. But if you select this boundary and do calculate PDF table, additionally there will be a mixture of all the species, around 20 species will be added. Okay, so this way we are including the fuel air mixture species we are including. The next step, in the boundary condition, if it is normal cold flow, what we will do, just we will define the what is the momentum velocity. As it has both air and fuel, we are defining the fuel velocity also. So velocity we will define normally. Then temperature we will define. So here I have taken 650 Kelvin for air, 300 Kelvin for fuel. Why they have taken more temperature means normally the combustor inlet, which will be the compressor outlet. So normally the pressure will be minimum at least to 10 bar. It may go to 20 bar, 30 bar, also depends upon the engine. So minimum 10 bar high pressure with a high temperature. The temperature varies from 600 to 800 Kelvin will be there. So normally for the combustor they may take air inlet with a high temperature and fuel with a normal atmospheric temperature they will take. So like a previous exercise and all, simply you will define the velocity, also the temperature of air and fuel. Now as we enabled species in this model, now the species table also enabled. In the previous version cold flow and all, this will be disabled. Now this also enabled, and by default there will be a 0 0 value for this mean mixture fraction etc. and all. So how the software designed, so if it is with a 0, software will consider this as a air or oxidizer. Okay, so if it is with a 1, then the software will consider this as a fuel. Okay, so if you forgot to define mean mixture fraction as 1 for at the fuel inlet, what will happen? So we have taken 650 Kelvin and 300 Kelvin, right? So if it is not defined as a mean mixture fraction 1, it will be like a normal mixing flow. So with the 650 and 300, just it will mix, we may get just over 500 Kelvin temperature only will get it. But if you define this mean mixture fraction, then software will consider this fuel inlet as a fuel, whichever that we define, that will be as a fuel. Then there will be a reaction, combustion happens, so that the temperature will shoot up to around 2000 Kelvin. Okay, if you so from the static temperature only, first we will ensure either the combustion happened or not. So if you are getting only, for example, with these two temperature difference, if you are getting only 500 600, that means you forgot to define this mean mixture fraction. Okay, if it is defined, it will go to around 2000 Kelvin. Okay, so only this is different compared to the other cold flow. Okay, almost everything is same. So we will define the species in the model. Similarly, in the velocity inlet, we will define the species. This alone different compared to the cold flow. And see, similarly, in the contour, normally you will check the pressure, temperature, etc. and all. Now, as the species is enabled here also there will be a species option. With that, you can see what are all the reactants we have taken, what are all the products we are getting, everything you can see. So here they have seen the water vapor formation. So there is a reaction happened. That's why there is a water vapor formation happened. That also you can ensure. So normally we will check static temperature, so which will reach closer to the 2000 Kelvin. Then we can see fuel fraction. Then what are all the product H2O or CO2 whichever available. Additionally, we used to see radical H or OH radicals, which will show the flame core. I think I have the image next to it. You can see after the combustion, the temperature reached to 2219.85 Kelvin, and these are all oxidizer fuel. Here you can see due to the combustion there is a H2O water vapor formation, and this is a radical of H or OH. You can see there is a flame core. Like that, everything you can see. Then just some introduction. So normally combustor, if you see, it will be with a circular cross section like a cylindrical shape. So this is the 3D one. So this is the air inlet. This is these two are the fuel inlet. For example, I have taken. So instead of 3D, if you want to simulate this as a 2D, what we will think? Just we will cut it in the center so that this kind of flow will get it. So this will be the air inlet. Above and below there will be fuel inlet. This is open to the atmosphere, pressure outlet. Like that you will define. But as it is a axis symmetrical model, with a circular cross section, we should not go for the planar, we should go for the axisymmetric. Okay, so this will be the air inlet, this will be the fuel inlet, then this line will be the axis, this is the pressure outlet, this is the valve, like that. So normal combustor, if you want to simulate, you should go the 2D way. If you want to simulate, you have to choose the axisymmetric only. Similarly, if it is a swirl combustor, that is, this will be the fuel inlet, then outside there will be a swirl vanes which is creating the swirl, which is giving the swirl component, tangential component to the flow, so that it will be like a swirl flow within the combustor. So this kind of swirl combustor, if you want to simulate, then you should choose axisymmetrical swirl. Okay, you should not go with the regular combustor model like a axisymmetric. Whenever there is a swirl, then you should go for the axisymmetrical swirl. So other things are same. So like this is the velocity inlet, this is the air inlet, valve, this is axis, this is the pressure outlet. Everything is same, but in the 2D space, instead of axisymmetric, you have to go for the axisymmetric swirl. The reason is, so if it is the axisymmetric, in the velocity inlet, we can define only axial and radial. That is, what is the x component, y component alone we can define axial and radial. But as we if you want to define the swirl combustor, then there will be a tangential component, swirl component, that you can define only in this option. So here, if you open and check the velocity inlet, there will be additionally swirl velocity, which is the tangential velocity. This component also will be enabled. Okay, so if there is a swirl combustor, swirl component, you should go for the axisymmetrical swirl. Otherwise, it will be like only 2D x-axis, y-axis only you can define. Okay, so with the swirl means axisymmetrical swirl you have to choose. Just I have shown the swirl combustor. See, the center one is the fuel inlet. Outside there is a swirl vanes which is giving the tangential velocity to the flow. So this is the air inlet. So because of this swirl injector, we are getting the spiral flow within the combustion chamber. And if you take this in a 2D, then I will define the axis here. Okay, and this will be my fuel inlet, then this will be my air inlet, and these are all valve, then this will be a pressure outlet, and this line will be axis, like that I will define. Okay, so this is the fuel inlet, this is the air inlet, then these are all valve, this is the pressure outlet, this is the axis. So this way only we'll give it, we will take the 2D domain. So same thing I have taken. So here I have the fuel inlet, next there is a small valve, then there is a air inlet, then these two are valve, then here it is pressure outlet, this side axis, like that I have taken. So as I am taking fuel and air separately, it will be a non-premixed, and as it is a swirl, so I will define both axial velocity and tangential velocity for the air inlet. Okay, only this much is different. So just the 2D domain I have shown here. Okay, just a single sheet. Then using this horizontal line, I divided into 4 blocks to define fuel inlet, air inlet, etc. and all. So as I mentioned, either you can take the hydrogen as a fuel or any hydrocarbon as a fuel. Hydrogen means only water vapor. Other hydrocarbons, there will be a water vapor and CO2 you can see. And swirl number. So this is the formula for the swirl number. This is a simplified one. It is simply a tangential velocity divided by the axial velocity. So normally this swirl combustor we are using mostly in the gas turbine turbofan engines. So the swirl number number will be approximately between 0.6 to 0.75. Okay. So by introducing this swirl, what is the purpose means? We are giving the proper mixing and combustion. Okay. The purpose of the swirl injector is the creating the proper mixing and combustion. Okay, this is just introduction. Okay, here I have shown just some existing paper with a swirl combustor. So the first one is the experimental data. Then here they compared results for the different turbulence model. So by default it will be k omega SST. Then they changed it to standard k epsilon, realizable k epsilon, etc. and all. You can see the results are almost the same only. So we can also take just standard k epsilon instead of default k omega SST, because k omega SST compared to the k omega SST, k epsilon will take less iteration to solve. Here also they have shown this is the temperature contour, this side streamline pattern with the velocity colors. Here also you see there is no much difference between the SST k omega and standard k epsilon. So we will try with the standard k epsilon, and here they have shown how streamline pattern temperature varies for the different swirl number. So this is 0 swirl number, that means there is no tangential velocity, only axial velocity. So both air, fuel, simply it is leaving the combustion chamber. Then keep on, we are increasing the swirl number. As the swirl number increases, there is a much tangential velocity. So there is a strong recirculation region which is ensuring the proper mixing and combustion. Okay, this is about the introduction. Now we will go to the software. So this is the that 2D domain that I have taken. Okay, so initially I have made a complete rectangular profile, then just I have done a vertical line, then using that split option I have divided this into finally 4 blocks. Okay, so this will be a fuel, this will be the air inlet, completely pressure outlet like that I have divided. Then in the geometry I define the defined all the boundary conditions. So this green color line is my fuel inlet, then this is my air inlet, then this small wall and these two wall as a wall I have taken. Okay, these two and this small line I have taken as a wall. Then the bottom is as a axis. Then these 4 lines are the pressure outlet. Okay, this is how I define the name. Then mesh generation. So first step I will give the face meshing. Then I defined like for this, for the bottom line I given just 10 divisions, the next line just 5 divisions, then above that just 60 divisions, then above that 30 divisions with a bias factor 4, that is fine near this air inlet I have given. Then finally this horizontal line I defined as the equal interval 120. Okay, so with that I got this kind of mesh. But normally what happened here, almost for all the line I use the hard. See this, I will change it and show you. So what will happen by default, if you are defining the edge sizing, okay, I will show separately also otherwise. Okay, for example, just right click sizing, you can see what we will do normally. For example, these 4 lines I am defining, 5 lines I am defining the mesh divisions. I have select all the lines, apply, then here I will choose the number of divisions. For example 120 I mentioned, right, 120 divisions I applied, and I am not applying any bias factor, so with that I will leave. Okay, this I will delete it. Just now if you generate, you can see the lines, it is not straight. You can see this area, it is little bit inclined here and there, it is not proper. Okay, so in that case what we have to do, this capture curvature, it is yes, right, this you make it to no. Okay, then you can see this behavior in the previous version and all, this behavior option will be visible by default, but here in the newer version it is hidden. Once you give no to this capture curvature, then this option will be enabled. So by default it is a soft, that means whatever you define, software will not take it completely blindly. Okay, it will check the geometry, according to that it will adjust. Okay, so instead of the soft, if you give the hard, now software blindly will take whichever the condition you are taking. Mostly for the I used to give for the aerofoil simulation and all. On the aerofoil I used to go for the hard, otherwise there will be lot of sharp edges and curvatures. So this you may define for example 100 divisions with a different bias, but software will adjust, it may take different divisions and different bias also. So instead if you give hard, whichever we are defining, same thing we can get it. For see, now I am generating. Now you see everything is as a perfect straight lines. Okay, so whenever, even though after defining the face meshing and proper edge sizing, if it is not coming straight, then you change the capture curvature to no, then behavior to hard. This way you can rectify this mesh error. Okay, so this much mesh I have taken, just a coarse mesh only I have taken. Okay, so I change, once again I have to update. So at last you have to update. Now you can close. So here, then we will go to the setup window. So in the setup window, so the first option, so here we are taking only the what is it, subsonic flow only. So I can go with the pressure based, and this is not a planar, and I am going to simulate the swirl combustion. So I have to go for the axisymmetrical swirl. I will show you how the velocity inlet varies for this axisymmetrical and axisymmetrical swirl. For example, first I am choosing this axisymmetric. Okay, now if you check this boundary condition, for example air inlet velocity, if you check, by default it will be magnitude and normal direction, which will show only the one velocity component. Instead of magnitude and normal to boundary, if you change this to the component, then you can see axial velocity, radial velocity. Okay, like that in the axis symmetrical you can define only the x and y direction only, we can check, we can define. Okay, so instead if you go with this axisymmetrical swirl, now if you check the boundary condition, the same air inlet, so by default it will be like a magnitude and normal to boundary, so only velocity option will come. So now if you go to component, you can see axial velocity, radial velocity, additionally swirl velocity also will be there. Okay, so this swirl velocity will be enabled only with the axisymmetrical swirl. Next we have the angular velocity. Mostly this we will use it for the 3D. Okay, but now we have taken only 2D, so we will define only axial and swirl velocity here. Okay, so I have taken pressure based and axisymmetrical swirl. Then in the model we will check the energy on, then viscous model, simply I am taking the standard K epsilon. Okay, so default will be K omega SST, I am taking just a K epsilon standard model. Then you have to check this species. Okay, so select the species. So first one is not the combustion, just mixing, we can see remaining and all for the combustion. So I will choose this non-premixed combustion, as we are taking air and fuel separately. So first step will be going to the boundary. Here we will define. Okay, already the oxidizer mole fraction is already defined. So either if you want, you can define 1 for the hydrogen if you want to take this as a fuel, or if you want to take CH4 as a fuel, then you have to define 1 here, or any other parameter if you want to include, you can type here. Or if you want to check, you can just press list available species. You can see these many available species are available in the library. Okay, anything you can choose, around 700 species, 600 species available. Okay, so here I will choose fuel as methane and proceed. Okay, and temperature also just I am not changing, I will leave it with the atmospheric conditions. We will see with this 300 itself, due to the combustion the temperature is increasing towards 2000. Otherwise normally the oxidizer temperature will be high, it will be around 600 to 800 between that. Okay, just for the demo I am just leaving this with 300 only fuel I defined. So this is the boundary table. Next I am going for this table. So here you have to select calculate PDF table. So it is calculating the other species related to this combination. So calculating the PDF table. So using this probability density function at calculator and added the 20 species. Okay, so where you can see this means I will show you. Okay, so in the species model, non-premixed fuel fraction, mole fraction is 1. The table, simply press calculate PDF table and OK. Now you can see in the material, previously only air and solid. I think mistakenly dealt the air. So now we have taken the mixture. Okay. Now we can see all these species are intruded because of the this PDF calculate. Then you will go to the boundary conditions. So first is the air velocity inlet. Air inlet I have taken. So axial velocity I am taking 20. Swirl velocity, if you give some 0.7 something, it may be 12, 13 something will come. So I will give for example or 13. Okay, swirl velocity 13 or even 15 round value, just I will take it. Okay, so axial velocity, additionally I define the swirl velocity also. Then thermal temperature I am taking just 300 only. Then species also enabled. Here I am not changing. This is the air, so it will be 0 0 only. Okay. Then fuel inlet, same way we will define the velocity. So I have taken just half of the velocity. There 20, here just I have taken 10 meter per second. Then temperature also same temperature. In the species, by default it will be 0. You should define this as the 1. Okay, wow. If you are not changing this as a 1, combustion will not happen. So in the fuel inlet, mean mixture fraction should be 1. Then normal pressure outlet, wall, etc. It is same only, and this is axis. So these are remaining and all same. Then what you will do? We will compute from the air inlet. Normally the reference zone will be from the empty. Like that you will start. Then in the method, I will enable all these options. Okay, because if there are any warped phase, relaxation, etc. I am adding, so that with easily the solution will be converged. Then you can initialize from the air inlet, initialize, run for maybe some 1000 to 3000 iteration. Okay, so I have to run now. As I changed the mesh, so the result already I finished the running here. Run here. As I changed, I have to do it once again. So just for the demo purpose, I just stopped with some less iteration. Now if you check this contour, so you will first check the temperature. Okay, you can see the temperature. It reached up to 1801 Kelvin. Okay, I just taken only 300 Kelvin only. Due to the combustion happen, the temperature reached to 1800 Kelvin. Okay, so this is the temperature profile. Then additionally we can see the species here. Okay, so this is the fuel. Okay, mass fraction of CH4 you have taken, right? So that we can check. Okay, up to that the fuel we are seeing. After that there is a combustion, so there is no methane. It is becoming a H2O, CO2, like that the products we are getting. So only up to this the fuel is extended. This is because of the swirl injector. If there is no swirl injector, then the fuel will be extended. Up to that there is no combustion, that is very slow combustion. Then only proper combustion will occur. That also I will show. So because of the effective swirl with the short distance itself, fuel the combustion happened. So there is no fuel, only product we are seeing. We can see the H2O. You can see from here itself there is a product, water vapor formation, then CO2. Okay, then if you want you can check the radicals of OH or H, where there is this is the flame core. Okay, like that and all you can check it. Additionally, if you want path line also you can check. So normally by default value will be the path line. If you open, it will be 500. Here it will be 0. This will be the path line. Here it will be by default particle variables. So I am checking this as a temperature, and on which, for example, you can select everything also. Everything you have to select, and don't give 500 because it will take very fine lines. Okay, it will take much time. So I will go with a very less number, maybe a 20, 30, like that I am giving. Now you display. See, this is the streamline. Even with the 30, it is very fine, right? I couldn't see. So you can reduce this size, or you can skip. For example, you see, I will skip 10. You see, you can see, okay, around 10 lines skipped like that. So some lines we skipped. So these are all the recirculation region. Okay, so because of that, there is a proper mixing here. Now we will see without that swirl. Okay, without the tangential velocity, how the combustion happened. You can see combustion started at the beginning itself. So the fuel we have seen only within this region. Okay, within the short distance only fuel we have seen, then combustion happened. Now we will see, for example, here itself I will go with a 0 swirl. Okay, there is no swirl, like that I will give. Once again, I have to go with a reference value from air inlet, this reference zone from this empty cell, then initialize from the air inlet, then run calculation. So just again with the same iteration, for the demo purpose I stopped. So now we will check the contour. So we will first start with the temperature. Now you can see previously the combustion happened next to the inlet itself. Okay, but here you see it is happening next to the near the outlet. Okay, so here and there is no combustion at all. We will see the species. First fuel we will check. See, previously within this short distance fuel got confined. Immediately after that there is a combustion, so there is no fuel extension. But here up to that there is a fuel. Here after only there is a combustion, like that it is extended, so that here there won't be any proper mixing and combustion. It will be like incomplete combustion. So to create the proper mixing and combustion only, we are going for the swirl combustor. So you will see H2O formation. You can see it is only at the exit. Then CO2 formation. Then you will see where is the flame. You see flame is at the exit. Previously it was next to the inlet. Okay, so that there is a better combustion, like that. You can compare with the swirl, without swirl. Okay. So if it is, there is no swirl component, just fuel and air inlet alone if you are taking, you can go with the simple axisymmetric itself. Okay.